Hello students, my name is Shashank Shekhar and today is the last lecture of the chapter Aldehyde Ketone and Carboxylic acid. So today we will be seeing the reactions of the carboxylic acid. Basically, if you look at the syllabus here, so we have covered this part, that is the nomenclature and preparation part. Okay, so we have seen the preparation and nomenclature of carboxylic acid. Today we will be dealing with this acidic nature first of all. So we will seeing this acidic nature because this acidic nature plays a huge role in the reactivity of the carboxylic acid. Okay, so we are done with this thing, and remaining part is this chemical properties. Okay, so today we will cover this part, and we will finish the theory part of the chapter, that is aldehyde ketone and carboxylic acid. So let us look at the topics of today. So as I have told you earlier, so first we will look at the acidity. So if you look at the name of the carboxylic acid, it ends with the suffix that is acid. So it must be related to its property. It is named. Why is it named so? So we'll see to it why is it named so. Okay. Then we will do the quantitative analysis of the acidity. That how can we put a measurement scale on the acidity? What are the parameters that can be used? That we can use. Talking of that, we will see pKa. Okay, later on we will see the qualitative analysis. Basically, we will seek the effect of substituent. So as we introduce more and more substituent on the carboxylic acid part, we'll see the acidity variation. Then we will move to the illustration, that how this say effect of substituent can be understood with the help of some examples. We will see it. After that, looking at all of these, which are basically the reaction which are involving the cleavage of the OH bond, because each of these is facilitated by the release of H+, that is acidity. So if you look at the carboxylic group, it looks like this, and we have the alkyl part here. So what are we doing? We are facilitating this H. So basically we are breaking this bond here. Clear? So therefore we were looking at the cleavage of O and H bond. After that, we will move to the cleavage of this CO bond. So this bond basically, so we'll look at the cleavage of this bond, in which we will see the formation of anhydride, esterification, reaction with thionyl chloride and ammonia. So in all of this, different type of derivatives of carboxylic acid will be formed, starting from anhydride, moving on to esters, and this will form acyl chloride. Acyl chloride. Okay. If you are talking about acidic acid, we will form acyl chloride, and depending on the substituent, that the carboxylic acid that we are using, we will get different type of chlorides, carbonyl chlorides, I would say more appropriately. Then we will see the reaction with ammonia that will result in the formation of amide basically. At last, we will see Hell-Volhard-Zielinski reaction. Basically, it is a name reaction in which we introduced a halogen group at the alpha position, means with respect to this carboxylic group, the alpha carbon will be substituted with this halogen group. Okay, so let us start today's class. So let us start first with the acidity. So as I have told you earlier, so acidity means we are facilitating this H+, and the ease with which this OH bond can be cleaved will basically define the acidity of the given carboxylic acid. Now, as we have seen that it has a suffix acid with its name only. And why is it so? The reason behind it is very simple, because as compared to all other functional group that we have seen till now, and we'll see, and compared to the functional group that we'll see later on, this one is the most acidic one. Whether we talk of amine, whether we talk of say alcohol, or say your halogen, which is haloalkane, which is not in the competition also with a. So when we talk of all of this, you will see that this carboxylic acid is the most acidic. And what is the reason behind it? We will see it later. Basically, it is a structural aspect. We will see it later. But for now, just assume that it is the most acidic of all of this. Clear? Now, let us move to the next thing. So how we will say that, okay, it is more acidic? So for that, what we have done some reactions, starting from the reaction with this metal, moving on to reaction with this sodium hydroxide, or we can say sodium bicarbonate, and depending upon the reactivity with this specific bases, we will define the acidity of the carboxylic acid in comparison with the other functional groups. So if we talk about the reaction with metals, then you know that this alcohols and phenols. So basically, if we talk about phenol, they react with this sodium metal to give phenoxide ion. We have seen this reaction earlier. So if you don't remember, let me draw it for you. So it looks like this. Okay. So what I was telling, that the carboxylic acid like alcohol evolve hydrogen with electropositive metal and form salt with alkali metal, similar to that of phenols. So you will basically end up with this kind of salt, O minus and Na plus, if you react your phenol with sodium hydroxide or any metal. With the evolution of this H2 gas, which can be say your indication that you have done an acid base reaction and your acid was your phenol. So both of the carboxylic acid, so if you talk about carboxylic acid, so it also reacts with this metal to give the corresponding salt plus the hydrogen gas. Okay, so at this part we are the phenol is par with this carboxylic acid. Now what are we doing? We are taking a weaker base, say we are taking NaHCO3, and then the reaction of carboxylic acid with NaHCO3 still gives you the carboxylate ion. So it indicates that although the base is weaker, it is the acid, since the acid is strong, it still react with your base to give the corresponding salt and water and carbon dioxide. But if we compare the same thing with the phenol, then this phenol does not react with this NaHCO3. So with the help of this reaction, you can distinguish the, say, your phenol and your carboxylic acid. So if you react to phenol with your sodium bicarbonate, you will see that there is no reaction because the phenol is not acidic enough. But when we talk about this carboxylic acid, it reacts with this NaHCO3, which releases H2O plus CO2 and your carboxylic salt. Clear? So this was about the acidic nature of carboxylic acid in comparison with your other functional group. Now let us compare this acidic, say, acidity with, say, we will try to quantify it. Okay, so before moving to the substituent part, so I was talking about the substituent part. So before moving to the substituent part, we will try to quantify it. So how can we quantify it? So what do? We react our carboxylic acid, or we can say we simply do the hydrolysis of the carboxylic acid, and we get a stabilized ion. How is it stabilized? You can see here that this negative charge that is formed upon the reaction with this H2O is stabilized over two oxygens. And this, both of the structures, as you can see, these are identical in nature. And this identical nature creates a very stable structure for this carboxylate ion. So if any two structures are identical to each other, then the corresponding species will be very stable. So due to this reason, due to the, say, this kind of equivalence resonance, it is called equivalent resonance, this carboxylate ion is very stable. Now the resonance hybrid can be summarized with the help of this diagram, in which you can see that the pi bond is delocalized over both of these bonds, CO and this CO. Okay, and means you can say that this negative charge and the pi bond is delocalized over this three atoms. It will be written in the form of this equation. So you know how do we write this K equilibrium? Very simple. The reactant concentration, the product of the reactant concentration, which each of the species raised to the power that is equals to the coefficient in the given equation, divided by the product of the concentration of this product. Okay, product of the concentration of the product, with each is similarly here also the each species is raised to the power which is equal to the stoichiometric coefficient of the given species in the reaction. Now the reaction that we are given is, or the chemical equation that we will dealt with is this. Okay, so what are the reactants here? The reactants are carboxylic acid and water, and the product is hydronium ion and your carboxylate ion. So the product of the product, basically the product of the product is this, is written on the outside, that is a carboxylate ion concentration multiplied by H3O plus ion concentration, divided by concentration of water that is present on the reactant side multiplied by the concentration of carboxylic acid that is present on the reactant side. Okay. Now what are we doing here is that since this H2O, so whenever we do a hydrolysis, we take a large amount of water. Okay, clear? Now due to this large amount, so here you can see that we have taken water. So this is taking large amount. Now due to the large amount, the change in concentration, so if you look at the change in concentration, it is basically very less. Okay, so you can say that the change in concentration is approximately equals to 0, approximately near to 0. Now due to this reason, the concentration of water can be considered as constant. And what do? We take this constant H2O here in this side and multiply it with the K equilibrium, which is also a constant at the given temperature. Now when we multiply these two constants, we name it as the third constant, that is our acid dissociation constant. Now you have learned this acid dissociation constant in the ionic equilibrium part. No problem. You can relate the same thing here also. It is the same concept. Only in this case, we are applying it to the organic chemistry. Clear? So how do we write this? So since this H2O is transferred here, so what are we left with? We are left with H3O plus. Okay, clear? RCO minus. Clear? Then this carboxylic acid concentration. Okay. So at this part, we are done with this K dissociation constant. Now we can use this dissociation constant for the quantitative analysis. Good, no problem. But the difficulty with this dissociation constant is that it comes along with some power, like 10 to the power minus 11, 10 to the power minus 12, 10 to the power minus 14. And this makes it difficult for the comparison. So suppose you have a whole number 2, 3, 4, 5, 6. Now that would be easier to compare, as in comparison with this K that includes a power. So just try to engulf this thing, or just try to theoretize this thing by yourself, that if you take some value that is numerical or integer, like, or you can say not integer, I would say some rational number 2.3, 4.4, like that, where without much say difficulty you can remember it, while or you can say you can compare it. But if you compare it with this K value, which is always like 1.1, 10 to the power minus 13, 10 to the power minus 14, now this would make it difficult to compare, or you can say difficult to analyze. Now for that reason, we have introduced something that is called pKa. Okay, pKa. What is pKa? It is simply the negative logarithm of your acid dissociation constant. No more, no less. Just keep it in mind. What is pKa? A negative logarithm of your Ka. Now, what is the relation? Means it is directly proportional, or is it inversely proportional? Is this pK directly or inversely proportional to K? So if you look at this equation here, so this equation is saying that first you are taking a log of K. Okay, no problem. As the value of K increases, the value of log K increases. Now what we have done, we have put a negative sign against it. So what does this suggest? That as this K will rise, this whole value will decrease. How? First this will increase. Now we are taking a negative of that, means negative of increased value means a decreased value. So overall the value will decrease. Now you can say that this is called pK. So therefore pK increases if K decreases, and the vice versa is also true, that if K increases then pK decreases. So if you are given an acid, suppose you are given an acid whose pK is larger as compared to a different acid whose pK is smaller, so the one with the small pK will have the greater acidic property. Okay, clear? So suppose we see the pK of hydrochloric acid is minus 7.0. Okay, whereas the pK of trifluoroacetic acid is 0.23, benzoic acid is 4.19, and acetic acid is 4.76. Now if I ask you that given this value of your say pK, arrange them in the increasing of the order of the acidity, then how you will do it? Simply the one with the least value of your say pK will have the highest acidity, while the one with the greatest value of this, say the pK, will have the least acidity. Now, according to this theory, what would it say that, okay, acetic acid is the least acidic one, then comes your benzoic acid, and then comes your trifluoroacetic acid, and after that, the most acidic will be hydrochloric acid, as it is the most smallest one with a negative value. So this is the least one. So we can say that smaller the pK, the stronger the acid. Or you can say proton donor also, no problem. Better acid means the better proton donor. Now, strong acid. So if you must have heard this term strong, weak. So although these terms are relative, we cannot say this is strong acid. So until and unless we're comparing it with a third party, but still we are just putting a conventional way to define the strong acid and the weak acid. So if something is having a pK that is less than 1, then they are strong acid. Now the acid with the pK between 1 and 5 are considered to be moderately strong acid, and the weak acid are having which are having pK between 5 and 15, and the extremely weak acid are which are having greater than 15. So as we are increasing the value of pK, the acidic stress is decreasing. So less than 1 strong acid, 1 to 5 moderate acid, 5 to 15 weak acid, and less than 15, sorry, greater than 15 is extremely weak acid. Okay, clear? Now let us look at the effect of before that, let us do one more comparison here of different pKs. So what we will look at some examples here. So first, let us compare our carboxylic acid with mineral acid. Now only we have seen that the HCl has a negative value of this, say, your pK. So from that you can derive that this mineral acid are much more acidic as compared to any organic acid, whether it is carboxylic acid or whether it is trifluoroacetic acid. Still the mineral acid are the strongest one. But this acid is carboxylic acid are stronger than alcohol and phenol. We have talked about this. Now same thing written here, that the carboxylic acid is even stronger than all of this organic compound. And why is it so? We have discussed this, so we basically are summarizing it all. The conjugate value of carboxylic acid, that your carboxylate ion, is stabilized by two equivalent resonance structure. We have seen those. Now if you talk about the conjugate base of phenol, the first problem with the phenol conjugate base of phenol is that the negative charge resides on carbon as well along with the oxygen, whereas in case of carboxylate ion, the negative charge only resides on oxygen. So due to this reason, the carboxylate ion is stable. So first is the equivalent resonance, the major contributing factor. Then the lying of negative charge on an electronegative element, that is oxygen, second. And third, further, the negative charge is delocalized over two electronegative oxygen atom in carboxylate ion, whereas it is less effectively delocalized over one oxygen atom and less electronegative carbon atom. So in case of carboxylate ion, the negative charge is delocalized over only oxygen, both of the oxygen. While in the case of a phenol, the negative charge is stabilized not only on oxygen but also on carbon, which is not that much electronegative as compared to our oxygen. So therefore, due to these reasons, we can say that the carboxylate ion is a more stabilized phenoxide ion. Okay, more stabilized than the phenoxide ion. So carboxylic acid are more acidic than phenol. Okay, clear? So we are done with the comparison of your carboxylic acid with other functional group. Now let us try to compare the acidity by introducing different substituents. So what we will do, we will introduce different substituent. We will remove H and place different substituent like your nitro, yeah, like your fluoro, your chloro, and all of this, and we will see the effect of substituent on the acidity of this, say, different carboxylic acid. Let us first start with the say what is electron withdrawing group and what is electron donating group. First you should understand this. So the group which withdraws electron, or you can say which polarize electron clouds toward itself, are called as electron withdrawing group, which is generally abbreviated as EWG. Now the electron donating group conversely are the group which donate electrons. So that can be through various effects like a hyperconjugation effect or say a resonance effect, that is a different matter. So we are not subdividing it now. So what are we saying? That if something is attracting electron cloud towards itself, the electron withdrawing group, and if it is say repelling the electron cloud towards the other group, then it is called electron donating group. Now let us see some examples here. So first of all, before looking at the examples, now let us see what is the effect of this electron withdrawing group on your acidity. So if we have an electron withdrawing group, the acidity of the carboxylic acid increases. And similarly, if you have electron donating group, the acidity decreases. Now what is the reason behind it? The reason behind is that, so if we have an electron withdrawing group, then the electron withdrawing group will stabilize the negative charge. So what happens in a reaction? Well, what happens in acid-base reaction? The H plus is released. Now after the H plus is released, we have a negative charge that is being delocalized over carbon, oxygen and oxygen. So although it is delocalized, but still the negative charge is a negative charge. It cannot be neutralized with the help of just delocalization. Okay, so what do? We introduce the electron withdrawing group that will attract the electron density toward itself and will try to delocalize in a different fashion, I would say, but still it is delocalizing, or you can say stabilizing that negative charge. Now that could happen if and only if we have electron withdrawing group. Now suppose let us compare it with, say, our analogy of the society. Now if in the society there are rich people and poor people at the same time, now if we give money to the richer, then he will become rich and rich and rich, and take money from the poorer, then he will become poorer and poorer, and that would imbalance the society. Okay, now the same analogy can be applied here. So if we have something that has a negative charge on it, so if we say attach a electron donating group that is donating electron to it, that would destabilize the ion or intermediate. Okay, clear? So what do? We attach a electron withdrawing group to stabilize this carboxylate ion. Now let us look at the acidic order. Okay, the following group in the acidic order. So what happens if we introduce this CF3 or NO2 or CN and F on the alpha position? So what happened due to the introduction of this thing? So acidic nature increases in this fashion. Suppose we have CF3 COOH, then this would be more acidic as compared to if we have NO2 here. Then we have CN, F, Cl, Br, I, pH. So I would suggest that try to remember this series. Now it is understandable also that here we have 3 fluorine, so a carbon with 3 fluorine is more electronegative, so it will again act as an electron withdrawing group and stabilize your carboxylate ion. Then we have NO2, that is nitro group. Then we have CN, that is cyanide group. Then we have fluoride group, bromide group, iodide group, and at last we have phenyl. So phenyl is also a kind of electron stabilizing species through resonance, although it is weaker as compared to these electronegative groups, but still it is in the competition. Clear? Now let us try to make things more clear with the help of illustration. So what we have done, we have introduced different type of functional groups, or you can say different type of substituent at the alpha position, and try to compare the acidity. Then we got this kind of order. So the CF3COOH is the most acidic one. Then we have CCl3COOH. Then we have CHCl2COOH. So once we are done with this CF3, CCl3 and CHCl2, we move on to the nitro group. Now the nitro group is more acidic than this thing. Then we have CN group attached to this carbon. After that we have fluorine group attached to this carbon. Then we have Cl group. Then we have bromine. Means if you compare this thing with this upper one, so we have monohalogenated this compound, not dihalogenated. Okay, so if you started monohalogenating it, so fluorine would come first, then chlorine, bromine, and then H. Now we are introducing Cl here, but this Cl is far away from this COOH group, and this Cl is stabilizing the negative charge, means it was stabilizing the negative charge to inductive effect only, and inductive effect is distance dependent. So as we move this Cl group away from the major group, then your acidic strength will decrease. Then comes our benzoic acid. Okay, after that you can say phenyl benzoic acid, or you can say 2-phenyl ethanoic acid, this one. Then acetic acid, then your say this methane, ethane, propanoic acid. So propanoic acid, the least acidic one, because this is the electron donating group CH3 to plus I effect. Therefore, it is the least acidic as it will destabilize the COO minus that will be formed upon deprotonation of the carboxylic group. Clear? Now, let us move to a different type of cleavage of bond. So, up till now, we were discussing on the cleavage of the OH bond in the carboxylic group. Now, we will talk about the cleavage of the CO bond. Now, let us move to this type of cleavage. Okay. Now, talking about the cleavage of the CO bond, we will see 4 types of reaction here. First, formation of anhydride, which is basically reaction of 2 moles of the carboxylic acid. We will see this. Then we have esterification. Then we have reaction with PCl5, that is phosphorus pentachloride, phosphorus trichloride, thionyl chloride. After that, we will move to the reaction with ammonia. So let us first start with the formation of anhydride. So what are we doing? We are taking 2 moles of acetic acid. Here 1 mole and here 1 mole. And then we are treating this 2 moles with H plus in the presence of a dehydrating agent, that is P2O5. It is a kind of dehydrating agent. It removes water. Then we heat it in the presence of H plus and P2O5. Then what do we get is that this H2O has been removed. So basically here, this H2O has been removed. And we have formed a bond between the O and C. So therefore we got a anhydride, ethanoic anhydride. This group is called anhydride. So if you look at the structure of anhydride, we have C double bond O, C double bond O. In between these 2 carbonyl groups, we have the oxygen. In this type of functional group, it's called acetic anhydride. So here is an example of the preparation. Now let us move to the next derivative, that is esterification. So what is esterification? We treat our carboxylic acid with alcohols and phenols in the presence of mineral acid like H2SO4 and HCl. So say we have a carboxylic acid like this. Okay. And what do? We treat it with a, say we are treating with alcohol in the presence of H2SO4. Then we will get ester. Ester looks like this. So in place of H that was present in your carboxylic acid, we have R present here. Now you will say that, okay sir, you have told that we are talking about the cleavage of CO bond, but here you have cleaved OH bond. Basically I have removed H and replaced it with R. But students, see, this is not the way this reaction goes. In this reaction, what happens? This R-O will attack the carbonyl center of the carboxylic acid and will remove the OH part here. So we are breaking the CO bond, not the OH bond. It seems to be in the first view that, okay, we are breaking the OH bond, but it is not so. Now, why are we taking this acid? So we are trying to protonate, or you can say we are trying to just facilitate the reaction in the forward direction by increasing the nucleophilicity of the carboxylate group. Now let us look at an mechanism here, that how does the reaction go. So as it is written here, the esterification of the reaction is a kind of nucleophilic acyl substitution. Now first of all, the protonation will occur here. So as I have told you earlier, that H2SO4 will protonate your carboxylic acid or a carbonyl group. Now after protonating it, the nucleophilicity of this center will increase due to the positive charge that is being carried on the oxygen. Therefore your R-OH will attack, means the oxygen present in the R-OH is having lone pair, so it will attack the say vulnerable nucleophilic center. This will create this kind of structure. Now since the oxygen has donated one more pair of electrons, so it will carry a positive charge. So what will happen in the next part? The H will be transferred onto the OH, and further the removal of H2O takes place and we are left with this kind of group. Okay. Now, since it is an acid catalyzed reaction, you will get your H plus back and your ester as the major product. So this is the overall reaction. So what do we do in the reaction? We take a carboxylic acid, protonate it with H plus, do the nucleophilic attack of R-OH, then intermediate proton transfer, removal of H2O and the removal of H plus. So this is the overall reaction, that is the esterification reaction. Now next is the reaction with thionyl chloride. So although I've written thionyl chloride, we have more reagents like PCl5 or PCl3. Okay. So what is thio? First of all, thio stands for sulfur here. Okay. Thionyl chloride. For thionyl chloride, this is called thionyl chloride. Now what happens in this thionyl chloride reaction? So it is basically a kind of SNI reaction. The lone pair on the oxygen attacks the sulfur center and the Cl minus is transferred from the SOCl2 to the carboxylic acid and we get a acyl chloride. Okay. So here is the examples. Here's the examples. So we are treating your carboxylic acid with different chloride donors. Now you can see here that for PCl3 we are using 3 moles of your RCOOH. So this should be notified. Then for SOCl2 we have still 1 mole of the RCOOH. Now thionyl chloride is preferred because the other two products are gaseous and escape the reaction mixture. So you must have heard this sentence earlier where you have seen the preparation of your say chloride, where we are using the alcohol with the thionyl chloride and getting our respective alcohol. There also the other two substances were gases and the same gases, SO2 and HCl. Here also SO2 and HCl, and they will be evaporated and we do not need to further purify it to get our final product, that is the acyl chloride. Okay, clear? So this is also a cleavage of CO bond. Now if you want to look at the mechanism, you can go back to the lecture series that was involving your carboxyl alcohol. In the similar fashion, the oxygen lone pair will attack a PCl5 and Cl will be instead facilitated to remove the OH group. Clear? Now next, the reaction with ammonia. What happens with reaction with ammonia? Amide is formed. Now this reaction not happened in one step. First of all, our carboxylic acid is treated with ammonia and we get ammonium acetate. This is called as ammonium acetate. Sorry for writing it here. It will be written here. Ammonium acetate. Okay. Now, once we get this ammonium acetate, it is heated and H2O is removed to get our amide. This is called acetamide and its structure looks like this. Okay. Now let us take an interesting example to get a grab of this say reaction with ammonia. So we take phthalic acid. Okay, this is called phthalic acid, and we react this phthalic acid with excess of ammonia. Now upon the reaction of ammonia, we have seen that we form ammonium acetate in the case of this reaction. So similarly, we will form the corresponding ammonium carboxylate. So 2 ammonium carboxylate ion are formed, or 2 carboxylate salts are formed at the same compound. Further, we heat it and we got our CuNH2. So till this point, we are okay with the reaction. But what happens? Now we are heating it stronger. So instead earlier say we are heating at 40 degrees, 60 degrees Celsius. Now we are heating it with 100 or say 120 degrees Celsius. Now due to this, again NH3 is removed and we get the phthalimide. This is called as phthalimide. So in this reaction, what happens is that, so if we look at the mechanism, so we have CO, NH2 and we have CO, NH2. We have lone pair here, it will attack here and this will move here. No problem. Now, after moving to here, it will come back. Okay, come back and kick this out along with this H, so that we get NH3 also, ammonia released, plus phthalimide. Okay, so this was the reaction with ammonia. Now at last, we will see what is this Hell-Volhard-Zielinski reaction? So you must look at this reaction properly because it is a name reaction. So what do we do in this reaction basically? So in this reaction, we treat our carboxylic acid with X2 and red phosphorus, okay, and then hydrolyze it. Now the product that is formed is interesting. Why is it interesting? We get a halogen at a alpha position. Now if you try to look at the or imagine a mechanism, that would be very absurd. I would not do it in this class, okay. You can try by it yourself, but still this reaction is fun, okay. So we react our carboxylic acid with X2 red phosphorus and then hydrolyze it. After doing this, we will see that an halogen group is introduced at the alpha position. So this is the alpha carbon because it's the carboxylic group. So just adjacent to this carbon, we have the alpha carbon, and we have a halogen group that is being attached due to the reaction with X2 red phosphorus and H2O. Now the thing here to notice is that the both of the halogens that we're talking about are chlorine and bromine only. We cannot take fluorine or iodine. So these are wrong for the Hell-Volhard-Zielinski reaction. Okay, clear? So this reaction is called as Hell-Volhard-Zielinski reaction, or sometimes it is abbreviated as HVZ reaction. No problem. Okay. Now let us look at a different reaction which I have not mentioned here, which is called as decarboxylation. So what do we do in decarboxylation? We take RCOOH, our carboxylic acid. Now we treat it with Na2CO3, okay, and heat it. Upon this reaction, you will see that this RCOOH has been removed, COH will be removed, and we get RH. Okay. So in this reaction, we are removing CO2 completely. Therefore, it is called as decarboxylation. Now what happens if we take carboxylate ion rather than this carboxylic acid? What will happen? So if you don't remember, no problem. You must have learned this reaction in the previous class, that is 11th class. So it is called as Kolbe reaction. So when you treat your carboxylate ion with Na2CO3 and heat, you will get R and R. Means both of the R are coupled with each other. So for this, you will take 2 moles of your carboxylate ion, sodium carboxylate ion. So what is the difference between this reaction and this reaction? So if we take carboxylic acid, then we simply get alkene. No problem. Now if we take a carboxylate ion, then rather than simply getting an alkane, we get a dialkane of the same carboxylate group, R and R dash attached to each other. So this is called as decarboxylation, and this is called as Kolbe reaction. Now you can think of more reaction of the carboxylic acid if you want. You can think of the reduction reaction. Now when we say reduction reaction, we know that carboxylic acid is not very easy to reduce because it requires strong reducing agent. Now for that, what do we use? So if you remember the previous class, the strongest reducing agent that we have studied till date is LiLHO, which is called as lithium aluminum hydride. So similar to the previous reaction, it will just coordinate its aluminum or say aluminum with your carboxylate ion or carboxylic acid and then facilitate the hydride. These hydrides are donated there. Now, on contrary to this, we can use a one more reagent which does not work on your aldehyde or ketone, but it works on this carboxylic acid, and the reason behind it is because this species is electron deficient. Okay, the first point is that. So this is called boron, BH3. So if you don't want to use LiLH4, you can use this BH3. Now this BH3 does not reduce alcohols or say I would say aldehyde or ketone. The reason behind is that this BH3 works on the principle on the donation of electron. Okay, so first of all, the carboxylic acid donates electron to your BH3. Okay, now this BH3 reduces the carboxylic acid to your corresponding alkane. Okay, clear? So this was the reduction. Now one more reaction I am left with, we are left with, that is the benzene carboxylic acid, or you can say benzoic acid. Now, what do we do? What we have done earlier, I would say, we have seen various type of your say substitution reaction, electrophilic aromatic substitution reaction. So if you talk about the carboxylic group, if you look at the structure here, it looks alike that it will attract the electron because you have no lone pair on this carbon. Therefore, the electrons will be attracted in this fashion. So it will go here and it will go here. Okay, no problem. So what the species will be formed? You will have a negative charge here and we will have a double bond C O minus and OH. Now this creates a positive charge on this center. Now if you try to resonate this positive charge, you will see further that in relevance to this carboxylic acid group position, we have alpha, beta and gamma position, or you can say ortho, meta and para position. Now if you just delocalize the previous positive charge, you will see that the ortho position and the para position are much more electron deficient. What are they? They are electron deficient. Okay, the electron deficient. Now what will happen? Due to this electron deficiency, the electrophilic aromatic substitution will disturb. And although it happens, it will happen on the meta position rather than your ortho or para position. So this should be noticed always. So if we take a carboxylic acid, okay, if you take the carboxylic acid and do the electrophilic aromatic substitution, say with the help of chlorine, you will end up with this kind of product. Okay, clear? So this is about the electrophilic aromatic substitution. So with this, we have covered all the reaction of your carboxylic acid. So first we have started with the acidity. We have seen the factors affecting the acidity, in which we talk about the effect of substituent on the carboxylic acid. Okay. Then we move on to the cleavage, that is the cleavage of the CO bond, in which we have seen various reaction. We have seen esterification. We have seen the reaction with amine to form your amide. Then the reaction with SOCl2 or PH3 or PCl3 or PCl5 to form your again your chloride, carbonyl chloride. Then we have seen the reaction with, let's say, as another mole of the carboxylic acid, but in the presence of a dehydrating agent, say we have P2O5, to give the corresponding acetic anhydride. After completing this all reaction that involves the cleavage of the CO bond, we move to the Hell-Bollard-Zielinski reaction. In that, we treat our carboxylic acid with a, say, your X2. That X2 can be only Cl2 and Br2 in the presence of red phosphorus. Okay, then we got a hydrogen group. Suppose we have chlorine here at the alpha position. Now the alpha position is, again, I will tell you it again, that it is the carbon that is present at alpha position with respect to this carboxylic group. So if it is alpha, suppose we have one more carbon here, then it will call as beta. Then one more carbon, then gamma. So if you treat your carboxylic acid with X2 and red phosphorus, then you will get a alpha halogenated carboxylic acid. So this is called as Hell-Bollard-Zielinski reaction. So this was for today's lecture. So with this, I would end my lecture. For the next class, we will start with the amine chapter. So first, as usual, you will look at the nomenclature and structure. And there we will look at the basicity rather than the acidity. So till now, we have seen the basicity, acidity till now. But this amine is basic in nature. So we will look at the basicity of this amine. Clear? Thank you very much.